Hello class. So today I want to address first the blood typing assignment that you were given. Now one of the questions on there, in particular the last question, it gets you to think about, well, what would happen if you did a direct blood transfusion into somebody, right? When I say direct, I mean if I saw somebody at the site of an accident, I have, say, O negative blood, can I hook my artery directly up to their vein, right? Is that something we could do? Can I directly withdraw blood from myself and inject it into somebody else? Now, since I'm O negative, in this example, I would be the universal donor, right? My red blood cells have no antigens on their surface. Therefore, they will not be attacked by antibodies in the recipient. However, and some of you picked up on this and sent me some excellent questions, what does my blood contain? What is in my plasma? Well, in my plasma is immunoglobulins, is antibodies, and if I was O negative, I would have antibodies against A and B antigen. So my antibodies in my plasma could attack the recipient blood, which is why when we donate blood, they spin it and they remove all of your plasma. They remove your plasma to avoid any antibody-antigen interactions. Now, in saying that, if you did a direct blood transfusion, it's not nearly as severe as receiving the wrong blood type. So my antibodies, yes, would slightly attack the recipient red blood, but likely the only symptoms you would experience is like a slight fever, for example. So really it's not going to kill you, but you will see a minor transfusion reaction if you do not remove the plasma from the blood, which is why we always remove the plasma when you go and you donate blood. So how do we measure electrical activity across the heart? Understanding this is important as we can get a lot of information about diseases that affect the heart by looking at this. So how do we do it? Well, we measure it with something called an electrocardiograph. This outputs the data into something we call an electrocardiogram. Now, you've probably heard this before. It's abbreviated ECG or EKG for short. In a medical setting, it's going to be EKG. I know there's no K in there, right? But the reason they call it an EKG is because it sounds too similar to EEG if you say ECG. EEG is an electroencephalogram, right? It's a brain scan, so they wanted to be clear. That's why it's called EKG. Now, your EKG has that characteristic, you've all seen it on medical shows, the beep, beep, right? Where the heart's electrical activity is outputted in this fashion here, where you say beep, beep, and the P, Q, R, S, and T represent different phases of your heartbeat cycle. So the P wave is going to represent your atria contracting. Now you'll notice there's a brief delay here before the QRS, which is where your ventricle is contracting, right? That electrical signal needs to go from the SA node, the sinoatrial node, across your atria, right? And that's causing them to pump the blood down, forcing them to contract. And then it gets to the AV node, the atrioventricular node, where it's going to go down the bundle of His and then up the walls of your ventricles, causing them to contract from the bottom up. So what you see here is this small electrical impulse. That is the P wave, the atria contracting. Then you have the QRS, which is your ventricles contracting. And then you have a period here where your heart is repolarizing. Right? It's getting ready for that next contraction. And that's what's represented here by the S and the T. So to reiterate, the P wave represents depolarization of the atria. And don't worry too much about that word right now. It'll make a lot more sense when we talk about the nervous system. But just know that your nerves are firing. That's pretty much what depolarization means. The PR represents the time the electrical impulse takes to get from the SA to the ventricles, right? SA to the AV node and then to the ventricles. Your QRS represents depolarization of the ventricles, aka the contraction of your ventricles. And the ST represents the period between depolarization and repolarization. And T here represents hyperpolarization. Again, these words will make more sense when we get to the nervous system, but just know that the ST segment is where your heart is getting ready to do the next beat, right? All of your nerve cells are getting back to their resting state so that they can fire yet again. Now, what happens if your heart is not working properly? Let's say the electrical system screws up and you develop what's called an arrhythmia, right? An abnormal rhythm to your heartbeat. And these can be broken down into two different categories. We can break them down into tachycardic events, tachycardia, where your heart is pumping too fast, right? Your heart is pumping too fast, and this does not allow your heart chambers to fill entirely, obviously making it less efficient, right? You're not pumping blood around efficiently, therefore you can get hypoxic. A lot of really bad things can happen. You don't want your heart to beat too fast. The other one is brachycardia, and this is if your heart is pumping too slowly. And again, if it's pumping too slowly or it's pumping irregularly, right, if you don't have your heart chambers in sequence with one another, this will again lead to poor efficiency, and thus you're not getting the blood where it needs to go. So let's say for a moment that your heart is completely screwed up, right? It's not completely tachycardic, brachycardic. It's entered into something called fibrillation, where the heart chambers have no sequence to their contractions. They are just randomly vibrating, right? You have the ventricles randomly contracting, the atria is randomly contracting, and if it's not in sequence, you will not get blood pumping at all, right? So if it's entered fibrillation, well, that is a really bad situation. We call this cardiac arrest. Now, unlike medical drama shows where they show the EKG completely flatlining, your heart has not stopped. What has happened is the electrical signals now are all jumbled. They're all mixed up. Your heart's just randomly contracting, and it's not contracting in sequence, in concert, and therefore blood is not pumping. So in this situation, the pacemaker cells are sending electrical signals faster than the heart can possibly respond, and the only thing that can restore what's called normal rhythm, sinus rhythm, is a defibrillator. And we all know what those are, right? The shock paddles, clear, give them a good old shock. And what is the point of a defibrillator? Well, this is going to put a strong electrical current across your heart, and it's going to cause all of your heart muscles to contract all at once, hoping that this will reset your heart and put it back into sinus rhythm, right? So one big shock that causes the entire thing to contract, and then when it relaxes, hopefully you return to normal sinus rhythm where your atria contract and then your ventricles contract, right? So that is what a defibrillator does. And we actually have one here in the school. We have an automatic electric defibrillator here at the school. It is quite interesting. I actually was going to contact the division and get a training one for this class where you could see how it works. It prompts you with where to put the electrodes, what to do exactly, and then it kind of shocks the person for you back into sinus rhythm. So that is all for this unit. The test will be posted and it will close next week. If you have any questions, do not hesitate to ask. Have a great day, everyone.